Okay, greetings students. There was a query with problem 7.2.15 about working out the correct normal stress and shear stress for the weld. This is in your Goodner book, the 9th edition, question 7.2.15. The problem is basically you've got a flat metal plate that is welded together along the diagonal. There is a stress in the x direction, stress in the y direction, and there's no specified shear stress acting on the plate. There's also some geometrical dimensions, a width and a height, and then the weld is going across the diagonal. The question is basically, given these particular initial conditions in the x and the y and the shear stress direction, find out the transform stress. That's essentially an application of the transformation equations for plane stress. If you look in your textbook, you find the following formula for sigma x, sigma x1, sigma y1, and tau x1, y1. So recall the basic sign convention. You've got an element in the initial stress state. Okay, this is your initial element. You've got a stress in the sigma x direction, you've got a stress in the sigma y direction, and you've got shear stresses on the sides of them. Recall the basic sign convention. Tau xy means it is acting on the x face in the y direction. Tau yx, it's a bit different. It is acting on the y face. This is the y face in the x direction. So this is your initial state, and obviously there's some coordinate system. There's an x and then there is a y. So that is your initial conditions, and then we assume there's a transformation. So something happens to the element, and the element rotates by an angle theta. This is your angle of rotation. Theta is positive in the anti-clockwise direction or the counterclockwise direction. So this is your initial axis, and then when you rotate it, you have a different set of axes. So that is your x. This is your x and your y axis. You rotate it by an angle theta, whatever the angle theta is. You have a new system of axes, an x1 and a y1, and correspondingly, when in the new coordinate system, you'll have new stresses. So you'll have a new stress, sigma xy and sigma y1 over there, and similarly you'll also have a transformed shear stress. So in this case you will have a, let's get this right, you'll have a shear stress tau y1 x1, and over here you would have a shear stress tau, it's the other way around, tau x1 y1 and tau y1 x1. Yes, that's right. Okay, in a similar sense, you have tau xy and tau yx. You would have the same system over there using the sign convention. Just remember the sign convention. If you have a general shear stress Ij, this means the face it is acting on, and J means the direction. You should go through your textbook to understand the sign convention. But in any case, let's move on. So the question was a bit confusing on how did we get the correct signs in the calculations at the end of the day. In the question, they gave you a set of assumptions that the normal stress, sigma W, is positive when tension is against the weld, and the shear stress is positive when it rotates in an counterclockwise direction. So we'll worry about the notations at the end when we're writing the final answer, but for now, let's just work out the calculations and see where it goes. So we've got the geometry, we've got a width, we've got a height, we've got the initial conditions in the right notation, where compressive stress is negative, tension is positive, and so on and so forth. Basically, we just use the geometry. And we have the angle over here. This is theta. Recall your basic trig identities. The tangent, tan, is equal to the opposite over the adjacent. And in this case, we're looking for theta. The angle, well, the dimension opposite theta is this thing, and that is 75 mils. And then the one adjacent to that is 125. So tan of theta would be 75 over 125. And then that means obviously theta would be the arctan of 75 over 125, which I calculate to be about 30.96 degrees, give or take. 30.96 degrees. All right, so far so good. So we've got the sigma x, which is plus 3.5. We've got a sigma y minus 2.5. No information is given on the shear stress. We assume it is 0. We plug in the data into the equations, the plane stress transformation equations. We get an answer for sigma x1 of, what is it? Sigma x1 is equal to positive 1.912 megapascals. Sigma y1 is equal to, what do I get? Negative 0.912, negative 0.912, and then the shear stress, I work it out to be shear stress tau x1 y1 is equal to minus 2.64 minus 2.647 megapascals. All right, so we've got the answers according to the formula using the equations. Now we just have to interpret what this physically means. Essentially, what happens is we look at the weld. The weld is obviously at some orientation. Now this is going to be my sigma y1, and then obviously that would be your sigma x1. According to our calculations, sigma y1 is negative 0.912. So positive would be going in this direction, okay? And then if it is negative, it'll be going in the opposite direction. So what happens is the normal stress is actually acting in this direction. So according to the problem, the stress is then a compressive stress. And because it's a compressive stress, according to our sign notation, it is positive when it's in tension. In other words, when it is positive is tension, physically pulling the weld. This is the weld, and then tension over there, but we worked it out to be going in this direction, so it's in compression. So if it's in compression, that means the normal stress, sigma W, would be negative. So our answer is sigma W is minus 912 kilopascals when we convert from megapascals to, this is your sigma Y. We're converting from megapascals to kilopascals to keep it consistent. That's the answer, and that's the reason why you get a negative normal stress for your weld over there. Now then, the other part is the sign notation. The shear stress is positive when it is counterclockwise. look through our sign notation again. Recall that. That's our sign notation. Our final answer at the end of the day is a negative shear stress. So if the stress is negative, it would be the opposite to a positive stress. What is a positive stress? In simple terms, a positive stress means when the shear stresses are going towards the corner, and a negative stress means when the shear stresses are going away from the corner. So if it is going away from the corner, we look at our stress element. Here's our element. This is our shear stress. It is going away from the corner, and if it's going away from the corner, that basically means it is rotating the element in a clockwise direction. So the shear stress is causing the element to rotate in a clockwise direction, and according to our sign convention, the shear stress is positive when it is in an anti-clockwise direction. Now, because the shear stress is causing it to rotate in a clockwise direction, it is going to be the other way around. So that will explain the sign convention. All right, so just think this through, and the trick is to work out the angle, put it into the formulae, and then the final part of the trick is to interpret what does it mean according to the sign notation in your assumptions. In most problems, you might not necessarily get this particular set of assumptions that it's positive against the world and it's positive clockwise, so we'll have to see what happens. All right, I think it's making sense, but look through it in your own time and then see if you understand it. Ask any questions on the website, and then I'll obviously try and answer it. That's the end. Thank you. Bye.